entitled Speed Science. So we have a variety of speakers to offer you. Science of chilies, volcanoes, astronomy, lots of different things. So I think I'll just talk a bit about our sponsors, and then we can get to it. Okay, so our main sponsor is Overleaf, and they are involved in helping scientists publish things better, essentially. So I've got some information about them here, and we'll be pleased to show you this at the end if you're very interested. Okay, so here is the schedule for tonight. We have a break around 8:40, and hopefully when we finish at 9 or at 9:30, there'll be time for you to get drinks and chat to the speakers then as well. So I'd like to introduce the first speaker. I'd like to introduce the first speaker.
You will.
So this is Becky Douglas, who's a PhD student in the Institute for Gravitational Research at the University of Glasgow. Becky is in the third year of her PhD, and her research is into novel materials that will be used, hopefully, to find gravitational waves. Becky does an extensive sort of variety of outreach activities and was a finalist in the National 3-Minute Thesis Competition. And she also writes a science magazine, Discs, which are filming tonight.
Yes.
So that's the next point I'm coming to. So maybe being filmed, be aware of this, and if you have any particular problems with it, then speak to the filmmakers and they will try to accommodate you. And we will also be taking pictures throughout the night. Okay? So I'll hand over to Becky just now. Just wait for this to get loaded up. Everybody excited about some science tonight?
Yay!
Fantastic. I hope you don't ask me any too difficult questions.
Is it? This one? That one?
Keep my fingers crossed I can answer. It's this.
Press play on the Hey!
Oh, would you look at that? Okay. As of this morning, there were 1,838 confirmed planets outside of our solar system. Planets that don't orbit our sun. They vary enormously. Some of them don't orbit stars at all, and we call those rogue planets, but the vast majority orbit some kind of a star. Some of them are so close to their star that they orbit in just a few of our hours. Imagine a year only a few hours long. Some are so far away that they orbit in a few thousand years. The largest is 20 times the size of Jupiter. It's actually causing a bit of an argument among scientists about whether it is indeed a planet or really just a small brown dwarf star. Astronomers argue over some pretty silly things. The smallest one is only a couple of times the size of our moon. They're curious, though, these planets flung across the Milky Way, and most of them are in the Milky Way. It's quite hard enough to find planets within our own galaxy, never mind looking further afield, although I think there are one or two. And so, why are we looking for these? How do we find them, and how do we make sure that we found what we think we have? And why should we care at all? We have a perfectly serviceable planet already. Why does it matter? Well, most of them are within 300 light years of the Earth, and that might sound quite large, but space is big, so actually it's fairly local. Space is famously big. And about 300 of them are rocky Earth-like, terrestrial planets. Things a bit like the Earth, things a bit like maybe Mercury, Venus, Mars, or maybe very different. What we've learned so far suggests that variety is king. These days we think that almost all stars have some kind of planetary system in orbit around them. So they're just out there waiting to be found. How do we find them? Well, there's a lot of methods. I've got time to talk about 3 of what I think are the most interesting methods. We have direct imaging, the brightness of stars, and watching stars to see if they wobble. Direct imaging is really, really hard. It means trying to look at a planet without being dazzled by its star. Now, most of the time, stars are going to be at least 1 million times brighter than their planet. So usually this works by having a planet that's really, really far away. So you can kind of block out the star, see just the planet, and maybe you can spot it that way. They're also usually huge, which obviously helps, and a lot of the time they're quite hot. That's useful because it means that we can image them in the infrared rather than the visible. The visible is just what you see with your eyes. The infrared is what you see if you're on CSI and you've put on that special green camera. It's just looking at heat. And in some cases, these planets are hotter in the infrared, brighter in the infrared than their stars are. So that helps. But it is really difficult. Sometimes it's more practical to look at the star brightness. For that, all you need to do is set up a telescope, look at the star, and wait. If a planet orbits it, then at some point it'll pass in front of it and cast a shadow. Now we're not going to see the shadow directly, we're not going to see the planet, but we are going to see a drop in total brightness, and that is enough to say, yeah, hey, there's a planet there, that's kind of cool. But it can take a while. To be absolutely sure, you need to observe that star before, during, and after the planetary transit. And really, you probably need to wait for it to come all the way back around so you can watch it transit again. Otherwise, maybe it was just an asteroid or a big cloud of dust, or maybe you blinked, or maybe your telescope needs a wash. It helps to have a friend watching as well so they can confirm what you've seen, but really, to be absolutely sure, you need to watch it twice. And that's all very well and good for those planets that orbit in a couple of hours, but if it takes a few thousand years, it ain't going to happen. So in that case, sometimes wobbling stars are better. This is illustrated beautifully with my diagram in the bottom there. This is also where I tell you something kind of planets don't orbit stars. It's technically true. Technically, planets, they don't orbit stars. Technically, planets and stars orbit a common centre of gravity, a common centre of mass. Now, stars are much bigger and heavier, so usually that's inside the star, but it's not in the dead centre, and that's the important bit. Because that means that while the planet is flinging itself around this star, it's exerting a force on it. It's dragging the star out of its comfort zone. And we see that as a wobble. So we stare at the star through a telescope and we see if it wobbles, and if it does, we can say, hey, there's something orbiting there. Maybe it's a star, maybe it's another planet, maybe it's something interesting. And then we can say, okay, so how close is it? How heavy is it? What's it doing? And that's all kind of cool. And through these methods, as well as others, often together, we've learned a great deal about what's out there. We found an awful lot. I'm very jealous of the kids. So that's kind of cool. And I think it's a testament, I'm sorry, this is my only graph, I promise. I think it's a testament to how quickly these days technology moves on. This is a graph that shows how many planets we discover every year. It starts in about 1988 and it finishes in 2015, although 2015 isn't coloured in yet because we haven't finished it. In the first decade, we don't find that many. Some years we find none. In a good year we find 1 or 2, maybe 3. But during that time we learn, we get better, the technology develops, we launch new telescopes, we get smarter, and we start finding them faster. We now find new planets at an exponential rate. So when I said, as of this morning, there are 1,838 planets, that's because by the time I finish this talk, there might be more. If I give this talk next week, there's going to be more. We find them quickly now. And so that's kind of impressive. Once we've found them, we need to decide if they're real. The International Astronomical Union provides the official definition of a planet. My solar system don't want none unless you're in orbit around the sun and you're approximately round and you've cleared your orbit. That's why Pluto doesn't count, because Pluto crosses orbits with Neptune and Neptune's bigger. Pluto can't win that fight, so it doesn't count. Kind of a shame. I think Pluto should be counted on historical grounds, but I'm not the boss, so fine. In terms of extrasolar planets, the definition gets hazy, like I said, around big gas giants versus teeny tiny stars. But over the next few years, no doubt, the scientific consensus will be reached, and that'll be firmed up, and some things that are currently planets will be discarded, and maybe some new ones will be added. And so it's quite an exciting time. For our purposes, if it's big enough to be found, it's probably spherical. If it's an orbit about a star, but it's not a star, it's probably a planet. Once we've found them, we need to categorize them. There's a few categories. I think the most interesting ones are hot Jupiters and super-Earths. Hot Jupiters are basically huge gas giants like Jupiter, but really close to their star, so they're hot. Now, because they're big, and because they're hot, and because they're close to their star, they're easy to find. Because they're easy to find, we find lots of them, and that's kind of cool. The other ones are super-Earths. Super-Earths are like the Earth, but huge, up to about 10 times the size of the Earth. Now, we do find some Earth-sized planets as well, and occasionally we find even smaller ones. But, again, being big is good. It means we find lots of them. And if we find a lot of something, we get to start asking some really interesting questions. Like, are any of these in the habitable zone around that star, the Goldilocks zone, the area where it's just warm enough that water will be liquid rather than ice, and just cool enough that it's going to be liquid rather than boiling off the steam? If there's liquid water, could there be life? Could there be something there already? Or if we wanted to, could we send life there? And if we did, would it survive? Well, the short answer is yes. Yes, there are rocky planets orbiting stars in the habitable zone. Yes, that means that if there's water there, it should be liquid. Yes, liquid water is one of the most important things when it comes to deciding whether or not life, as we know it, can survive. And you know, I mean, life is pretty weird, especially microbial, bacterial life. It diversifies to exist in the most unlikely of locations. We found bacterial life everywhere from Arctic permafrost to deep-sea volcanic vents. We found bacteria on the outside of the International Space Station. I should stress that because astronauts have touched stuff. It's not alien life, it's from Earth. But if it can survive there, maybe it isn't so weird to say, yeah, you could put life on this planet, or maybe there's stuff already there. But we haven't exactly made contact here. We've gone from saying, there is a rocky planet, and it's warm, to saying, it's probably wet. And we've gone from saying, it's probably wet, to aliens. No. It's hard enough to find a planet in the first place. We're getting better at understanding what's on them, so we can say, okay, maybe there's hydrogen, maybe there's water, but we're not sure. We don't really know, and it's going to be really hard to ever find out. But we're in the pub, we're having fun, so for the sake of our imaginations, let's speculate. This is the Kepler 62 system. It's kind of cool. It's got 5 planets. These are artist impressions. 2 of them are in the habitable zone. So, okay, so let's say that one of those 2 does have liquid water. Let's say it's got microbial life. Hell, let's say it's got intelligent life, little green men. Awesome. It's 1,200 light years away. Nothing can travel faster than the speed of light. Relativity is very, very strict on that. But even if it could, even if we had some kind of incredible spaceship that traveled at light speed, and we wanted to show someone to show up and say hello tomorrow, we needed to launch that spaceship in the year 815, when Bulgaria was signing the Treaty of 815 with the freaking Byzantine Empire. No one was launching spaceships that year. They were busy. If our friend on Kepler 62e did his tourism, wandered around, said hello to the locals, and decided to come back home, if he left this week, he wouldn't get back until the year 3215. I'm not sure that the human race will still be here in the year 3250. We'll be lucky if we haven't wiped ourselves out at this rate. So, not so great for a visit. It also doesn't really work for sending a message. You have to wait 1,200 years for the message to get there, and another 1,200 for it to get back, assuming there even is going to be one. That's a long wait. Even if we were to say, okay, let's be really exciting. Let's put a few hundred people in a spaceship and send them there. Well, they're not going to make it, but maybe their great-great-great-great-great-great-great-great-grandchildren might. That'd be kind of cool. But, I mean, so what? We're not going to talk to them. Like, it's not the best candidate. We need to seriously up our space travel and space communication game to a point where we don't actually think it's possible before this is useful. So we need somewhere closer. Is there anywhere closer? Well, yeah. There is a potential planet orbiting Alpha Centauri. It's only potential, but we're getting pretty good at this, so there's a good shot that there's a planet there. Alpha Centauri is only 4.37 light years away. Now, it's still not within space travel range. We're not going there. But you can send a text. 4 and a bit years there, 4 and a bit years back, 8 and a bit years for a reply. It's better than texting my mum. So, that's a bit more interesting. And yeah, if we really do up our space travel game in the next century or so, maybe we could send a probe. We started off imagining things that are impossible, but that actually kind of isn't. And that's quite exciting. This is the Hubble Deep Field Image. It'll be very familiar to any astronomers now. It's made by pointing the Hubble Space Telescope at one patch of sky and waiting, collecting light until all of this emerges. It's only 1/24 millionth of the night sky, so if I wanted to show you everything, I'd have to show you 24 million images just like this. And yet, every point of light here is not a star. Every point of light here is a galaxy, with anything from a few thousand to a few trillion stars. Each of those with 1, 2, 9, 20 planets in orbit around it. It's almost too big. It's kind of overwhelming. I think that mankind is in its infancy. I think that our first baby steps were understanding our own planet and getting curious about our moon and our solar system. And you know, we've done pretty well. We're getting down to the bottom of our oceans now. That's kind of cool. And we've put men on the moon. And we've sent robots all over the shop. We're doing all right. The Voyager probe has now left the solar system. So maybe that's a sign that our next step is to go beyond. And to go and see what else is out there. To start exploring just locally. At the beginning of the edge of our local galaxy. I think it's naive to say that our planet is the only one that's interesting. So I just hope that we don't lose our curiosity. Thank you for your attention.
So does anyone have any questions for Becky? You can ask them now, or
I'll be at the bar.
Any questions? Yep.
What's your take on the Fermi paradox?
Yeah, I think it's interesting, and I do think that we should talk about it probably at the bar because it merits more than general chat. Yeah, I mean, there's a lot of stuff published about this kind of thing, and a lot of things to speculate about and have fun with. We should come and find me. Sorry.
Any other questions? So, Becky, just quickly, do you want to tell us a bit about why you got into science in the first place? Or is that too big a question?
I got into science because somebody told me I couldn't. And I didn't like being told what I couldn't do. And it was interesting, and it was the most interesting thing to do at school. And I kind of then thought that physics was the most interesting part of that. And I got stuck. So that's kind of it for me.
Good answer.
Yeah.
Okay, I think I'm going to hand over to Anne-Marie now, but if you could all just thank Becky again for coming to speak.
So while we transition, if anybody's drink has run dry, you have a couple of minutes to grab another one. Or some chips, if you were jealous of chips during the last talk. You grab some of those.
Make it stop.
Cool. Well done. Good intro. That went well.
Was it?
Yeah.
I seemed a bit nervous.
No. It was good. It was good. So the next one is Sapphine, Thermal Break, or are you doing Bright Club?
Bright Club.
Sapphire.
So it's. Are you ready to go?
Yeah.
No, it's James.
Yeah, James.
There's a little bench up there.
Yeah.
I'll just give you There's no way.
Oh yeah. In fact, we should just put the sponsor thing up while we're waiting. Just leave it on.
Keep them happy. Know your sponsor.
Yeah.
Okay, we're gonna get started again since I think that was just hopefully enough time to get another drink. Our next speaker is from the Bright Club, which is a unique comedy night and public engagement activity in which academics present their research via the medium of stand-up comedy. It was founded at University College London in 2009, but has since spread to cities across the country from Bristol to Glasgow. We'll have 3 speakers from the Bright Club tonight, but the first one is James Taylor, who is a third-year PhD student at the University of Glasgow in the Cronin Group. His research is into understanding the chemistry of life and its origins, and he also enjoys historical fencing. He'll be talking to us today about molecular Glaswegians.
Good evening, everybody. My name is James. I'm a PhD in chemistry here at the University of Glasgow. And I've got to say, getting to study here is one of my proudest achievements. It took a lot of doing. I had to fill in this form. Name: James Taylor. I know. Sweet baby James. Program: PhD in chemistry, full time, 3.5 years. Sex? Well, if the above is anything to go by, I don't think the chances are very good. But really, it annoys me so much, these stereotypes that scientists are never getting laid. I mean, I'm not. I'm sure plenty of other ones are. Another big misconception that annoys me about science is that doing public engagement in science is glamorous. And I thought that. But then I helped out with a documentary that's being filmed in our lab, and I learned that being in a science documentary is a bit like being in porn. It feels really good, but no one wants to see your face. Third big, really annoying myth about chemistry that really annoys me is that making a molecule is like putting together molecular Lego or Kinects. And I thought that, but then I studied chemistry and I found out I've been lied to. In fact, making a molecule is not like putting together Lego or Kinects. It's a lot more like those foam letters that you get in the bath. So, imagine if you want to make a molecule, you want to do a chemical reaction, you take a bucket full of those foam letters, right? Chuck them into the bath. Throw in a rubber duck, because you can't have a bath without a rubber duck. Maybe one of them glittery bath bombs if you're anything like me. Don't judge. And then you get in there, and you thrash around like some crazy whale. And then you get out, maybe put some clothes on. And you get your colander, and you stick it in the bath, and you sift through, and fish out all your letters, and just hope that they've magically rearranged themselves to form your chemical outlet. In fact, a lot more likely you'll end up with chemical twilight. And sometimes I find you just don't get any words out of the bath at all, because the bath's turned brown and solidifies. Or the bath just caught fire. Or you try and stick your colander in the bath, but it dissolves because you fill the bath with dichloromethane. As does the ozone layer. But I've been at this for quite a while now. I've been trying to make this molecule, one tiny little molecule, just a smidgen of it, 6 months. 6 months I've been in the lab, and I haven't had any. I've not managed to make any of this molecule either. The kind of molecules that I'm trying to make are called amphiphiles. And an amphiphile is a bit like a molecular Glaswegian. It has a part of it which likes water, and a part of it that likes grease. And these molecular Glaswegians arrange themselves with grease on the inside and water on the outside. A bit like a load of people gathered around the munchie box on Stocky Hall Street in the rain.
That was me.
And it's these molecular Glaswegians which make up the membranes of living cells. So you could say that my research is tenuously connected to the origin of life. I don't just mean looking at my own sperm under a microscope. There are 2 kinds of scientists who use microscopes. Ones that have used them to look at their own sperm. And women. Well, once you've got your letters out the bath, maybe not all the words you want. Maybe, while you're in the bath, you're having a lot of fun in there, and your mum's copy of 50 Shades of Grey fell in there. Well, then that calls for some serious purification. And one of the most common ways of doing this is called column chromatography, which involves sitting there at the fume hood for about an hour, waiting for noxious solvent to drip into test tubes and rethinking your life choices. To explain how it works, imagine dropping off a busload of students at one end of Stocky Hall Street and collecting them as they get to the other. Naturally, the ones who've been on a heavy night out the night before are going to stop for a Greggs and they're going to arrive later. And that's the kind of separation you're looking for in chemistry. So, I like to have a lot of fun when I'm in the bath. My mum's copy of 50 Shades of Grey always falls in. Consequently, I spend most of the day in the lab with a massive column. This makes it very difficult to get any work done. But a saviour has arrived in the form of a fancy piece of new machinery. You put your sample in, and it runs your column for you. It is essentially a programmable undergraduate. Except this one's never hung over. It gives you, on a screen, a live readout of what's coming off your column when. And when this goes well, this can lead to a very exciting 15 minutes indeed. Ooh. It's got a touch screen. Oh yes, right there, take my sample! Oh, no, not there! Wrong injection port. Oh yes, right there! Oh, my peak looks so amazing! Just to point out, this isn't actually what I'm like in bed. You would give me a 2-hour set. Oh, here comes my product! All over those double E LSDs. Unfortunately though, when things don't go too well, it can spit out your impure product after a very disappointing 15 seconds. And it's worse when your supervisor's behind you watching. Honestly, this hasn't happened before! Please don't make me go back to doing it manually. I know what you're thinking. You're thinking this guy's just some pervert. But masturbation's just one of the things you can do when you're waiting for your reaction to finish. I am cultured a bit. I like a bit of music, so I've written you a few tunes. One second.
I'm essentially a human mind singing.
Yeah. I should have brought figurines. You hold it up, it's still okay. There we go. This is a song about when things aren't going particularly well in the lab. Let's fall off. Oh, that's not really good. Shit, right, guys.
I would sing some hold music, but I don't know.
Go for it.
Nah. There we go. Okay. I got my long needle, dry bag I swear. I got my spare boxes, I'll need them. Flask full of ether, organometallics, wrong calculation, failure, shit. My reaction's on fire. This is one about my love affair with a piece of laboratory glassware. Oh, I'm gonna pump you down tonight. Oh, I ran my sewer ceiling tight. You know what I'm gonna do? I'm gonna fill you with H2. Round bottom flasks, you make the rockin' world go round. And finally, this is a song about trying to find a chemical in the fridge in our lab. Hello, lab fridge, my old friend. I've come to open you again. Aiming bottles slowly leaking. Toxic vapors softly seeping. When my nose was hit by the stench of a rotting whale, as I inhaled and smelt the smell of science. And in the fridge's lights I saw 200 bottles, maybe more. If you don't label flasks of gunge, fuck you. If I don't find it soon, I think I'll spew. And I wonder why they only find me the next few days 6 feet away, because I'll smell of science. Thank you very much. Questions?
Did you find what you were looking for in the fridge?
Most of the time, you just gotta hold your breath before you open the door. Yeah?
Thrash around in the bath that help get rid of smell signs.
Sometimes. Well, if you kind of bath in vinegar, then that gets rid of the ammonia which comes from the fridge. But that creates its own problem. Yeah?
How big do you call them? No comment!
It varies.
Allegedly.
Yeah? Anyone else? Thank you very much.
Yay!
We're going to briefly switch speakers again, so you could grab a really quick drink,
That's good.
but you might miss something about volcanoes if you're too slow.
What are your straps?
Oh, it got pulled around this way, so it was going around the strings, and it was tied to mute the strings. So I just had to reconfigure it so it was around the body of the guitar.
Minor
around
detail.
the strings, yeah.
That's really good. And it's alright just to ask you a quick question. Yeah, just like, I've been imagining you to actually film you.
I think we're probably
It's meant to be a
I think it's good to give people a little break in between each
Oh yeah, it is.
Hi guys, if you could just find your seats, we're going to begin in like half a minute. Hello everyone. So I'm pleased to introduce one of our own Prime of Science team. This is Sapphine Wanmer. She is a PhD student in the Earth Sciences School at Glasgow University. She studies volcanic ash, and she has travelled around the world pursuing science, from the Mount St. Helens National Volcanic Monument in Washington, and to climbing Merapi, which is the most dangerous volcano in Indonesia, which is very interesting, so I hope we'll hear about that. She's also
She hinted.
She is also editor and columnist of an online science magazine called Experimentation. But I think I'll now hand over to Sapphine.
Thank you. So, unfortunately, you won't hear about Merapi tonight. But, so I'm a PhD student at the University of Glasgow and I study volcanic ash. So what is volcanic ash and how does it form? Well, it starts and it depends on the microbe chemistry on the Earth's surface. But I'm going to start off from the very beginning, just assume no previous knowledge. And I am going to talk about volcanoes, death, destruction, and life. So let's start off with then. The Earth's surface is broken into tectonic plates, and some of these collide, some pull apart, and some move cross each other. So most volcanoes form where one plate gets pushed beneath another at a subduction zone, and this plate that gets forced beneath contains water, which boils off and effectively melts some of the surrounding rock material. So these small pockets of melt rise to the surface and can accumulate and form a magma chamber, where it might get stuck in the crust, so the outer shell of our planet, or it can reach the surface and erupt. And this is the case for most of the volcanoes around the Pacific Ring of Fire. So we also have areas where the crust is pulling apart, and here we have lava that's erupting directly onto the surface, either on land or beneath the oceans. So that's a nice picture from Iceland, probably, and somewhere else. And this activity is occurring throughout the North Atlantic. But we also have some volcanoes that occur in seemingly random places. So like Hawaii here is in the middle of a plate, nowhere near these plate boundaries, so we don't have this subduction forming a volcano. So this volcanic region is forming in a hotspot, which might be related to a mantle plume, which is a hot, buoyant area of material that might be coming from the Earth's core. So, okay then, so what is the difference between this eruption and this eruption? What makes a volcano go bang? Because I'm sure that is what you want to know. Right, so I talked about the magma, and so that's quite an important thing in deciphering what happens when a volcano erupts. So for starters, we can have this magma and it can rise to the surface and get stuck and start to form crystals. So here we have, say, a magma chamber and it's crystallizing deep in the earth, and then our magma moves and it leaves some crystals behind. So, and then we have different composition of magma. So then this can erupt and it will erupt differently to the magma we had before. But then this could get stuck again in the crust, and it might eat or assimilate the rock around it, which then changes the magma chemistry again. We have these different magma chemistries depending on how long the magma spends within the crust and what the magma eats on its way to the surface. So actually the main thing that affects this chemistry is the silica content of the magma. So this is like glass or quartz, effectively, in the magma. And the more silica you have, the more sticky the magma will be. Okay, so sticky magma. So on the right or left, we have basalt, which contains very little silica, so not much quartz and stuff. And here we have a granite or rhyolite, which contains a lot of silica, so is very sticky. So this leads us on to the next variable that affects explosivity, and that's gas content. So, there we go. So, have you ever had the feeling after drinking a couple of beers at the pub where you feel like your stomach is expanding with the gas inside? So, at home, you might, arse wind here and there. And by the time you go to bed, you'll be feeling fine. But it's a bit, socially unacceptable in the pub, maybe? So you hold on to those gases and you feel your stomach build up and up and up until you feel like you're going to explode. Well, it's kind of the same for volcanoes. So with our different stickiness of magmas, if you have a magma that has less silica in it, it will easily let the gases escape from it, so it won't build up the same pressure. But if you have a sticky magma, it will hold on to those gases, so you get a massive build-up of pressure. And I'm guessing, as you all know, the longer you hold on to those gases, the bigger the explosion's going to be. Okay, so this is effectively... Oh, wait! I forgot my iron brew. So this is all effectively the same as shaking up your iron brew, giving it to your friend to open. So the gases inside, the pressure increases as you shake it, and the gases are expanding. But as you take the lid off, you're effectively releasing the pressure. The gases expand, fall, and fragment your magma or your iron rope, and that's your eruption. So this is like what happened 35 years ago yesterday at Mount St. Helens in Washington. So this is Mount St. Helens. That's nothing what she looks like at all today. So anyway, so this eruption occurred in 1980 and has inspired my whole life, although I wasn't born. Yeah, so I'm just going to tell you a bit about the eruption. So it started with a small earthquake that scientists originally thought was centered far away from the volcano, but they got this wrong. So they then researched this earthquake more and realized that it was actually centered right beneath the volcano. So then, in the next few weeks or days to week, there were more and more earthquakes beneath the volcano, and then all of a sudden we had a small, oh, there's your earthquakes. You had a small steam eruption which picked up material that was already in the volcano and just created this fantastic two-tone mountain. So we have ash on this side and the pristine white snow and glaciers on the other side. So this was the first activity in 123 years. It took everyone a bit by surprise. And the earthquakes were caused as magma was forcing its way up inside the volcano, and as it did this, it was fracturing the rocks as it went, so causing the earthquakes and small tremors. And the steam eruptions were probably caused by the contact of water or ice with hot rocks, not with magma, which is molten rock, but with hot rocks. So these are called phreatic eruptions. And these eruptions occurred recently at Mount Ontake in Japan, and can occur at any volcano or active volcano at any time. So, if you're ever visiting a volcano, you should bear this in mind, because these eruptions cannot be predicted. But anyway, back to Mount St. Helens. So we had these earthquakes and steam eruptions going on, and then the next development was the formation of this huge bulge on the side of the volcano. So this bulge was growing at 1.5 meters every day, so it's about my height every day, outwards from the volcano. So you can see here on that side, we have the volcano before anything happened, and then the swelling of the volcano. So scientists not only had to worry about an impending eruption, but they had to think about the possibility that this massive bulge on the side of the volcano could collapse in a very large landslide. So, but they said that if this happened, then it would occur like one that had happened at a volcano named Bondi in Japan. So at Bondi we had this collapse which triggered a lateral sideways blast, but this blast didn't reach particularly far outside of the volcano. But they said that that was the most likely scenario if the landslide occurred. So they formed a red zone around the volcano, which meant that only scientists would be allowed into this red zone, so some people had to be evacuated. And one man in particular, Mr. Harry Truman, lived by a lake less than 10 miles away from the volcano, and he, along with his cats, refused to leave his home. So he became a local folk hero, and he said that if the mountain goes, I'm going with it. The mountain ain't gonna hurt me. And he was reported to have been shaken out of his bed by earthquakes, and he's 83 years old. He moved his mattress from his bed and took it down to the basement for a better night's sleep. He received fan mail, which included many, many marriage proposals. So in the weeks before everything got real bad, we actually, scientists saw that the volcano went totally quiet. There was hardly any of these earthquakes and no steam eruptions, so magma stopped moving. So residents who had been evacuated about 2 months before decided that this was the end of activity and they started to rebel. They wanted to go home. So on May 17th, 1980, some people were allowed home to collect their possessions on the one condition that they were out of the area again by sunset. So I worked at Mount St Helens a couple of years ago and I met a man who had gone down to Spirit Lake, so less than 10 miles from the volcano, on May 17th with his friends to collect the Scouts' boating equipment from the lake. And they went down there and he said that May 17th was a beautiful, beautiful day. You could never imagine that the volcano would ever erupt. He said that because it was so nice, they were going to camp by the lake and return with their boating equipment in the morning. But as they settled down for the evening, a policeman arrived and told them to move immediately because the sun was setting and should be out by dark. So, after a bit of fuss, because they didn't understand why they should move, they evacuated. And if it wasn't for that policeman, none of those men would be alive today. So, at 8:32 on the morning of May 18th, 1980, suddenly the bulge on the side of the volcano failed in the largest landslide in recorded history. So this is a sequence of photographs taken from 10 miles away from the volcano. Wow. So the landslide occurred in 3 huge blocks, and that released the pressure just like removing the lid off of this shaking iron brew, and caused the magma inside to expand in a massive lateral blast. So this was much greater than the events at Bondi in Japan that the red zone was based on. And that's because at Bondi there had been no magma involved. But at Mount St Helens, as you can see by this nice red blob, we have a big amount of magma inside the volcano. So all the pressure in that magma of the gases in it was released all in one in this landslide. So this lateral blast overtook the landslide. It was travelling at 650 miles per hour. And could also be called a pyroclastic density current, which is a cloud of superheated gas, ash, and rocks. And this spread out to an impressive distance outside of the volcano and flattened everything within 12 miles and burned everything at a much greater distance than that. So as you can see, like trees just got absolutely flattened, looks like matchsticks laying down there, and just in the corner there's a small man for the scout. Well, he might not be a small man. We also had some melting of ice within the landslide deposits, which channeled this as floodwater down the local river valleys. So these are called lahars, and they contain everything, I think. So yeah, you just get destruction from these mud flows and lahars. And so there was a couple camping quite close to this river when this lahar struck, and they got swept into the river and crushed by an ever-increasing amount of trees. And they were both submerged at one point, and both thought that they were going to die. But both are alive today. So that's pretty good. But other people weren't so lucky. We had people dying from falling trees, the blast causing burns, and most people died from asphyxiation, which is breathing in of ash, which clogs the lungs. But there were some survivors. So the blast knocked down all the trees, and there was a group of students camping who fell into one of these hollows caused by a fallen down tree, and more trees fell on top of them, which protected them from the eruption. So this leads us on to, how do you survive an eruption? Can you do all of the things that they do in these films? So has anyone seen any of these films? Yeah. So does anyone know what this shot is from? No? It's from 2012. So the man is running away from one of these pyroclastic density currents, which is travelling at 650 miles per hour. And he jumps on a plane and is miraculously saved. No. I don't think that's going to happen. But anyway, so there are many stories of some fantastic survivals coming out of the most devastating eruptions. So for example, there was one man that survived this Mount Pelee eruption in 1902. He was actually a criminal, and he was found alive in his prison cell. So how did this man survive in an eruption that killed 25,000 people? Well, for starters, his prison cell was made of very thick walls, which meant that he was protected from the onslaught of all these boiling clouds and things, the pyroclastic density currents, and also that his building didn't collapse under a weight of ash. So he also, as you can see here, had very little air, so there were very little spaces for ash and debris to come in and harm him. So he walked free from this, and legend has it only 2 people survived this eruption, so he was incredibly lucky. So what else can you do? You can, the best thing to do actually is to cover your airways so that you don't breathe in the ash. You could cover yourself in damp cloths so you don't get burnt. But, oh yeah, and if there's projectiles coming down, you can run away, but look up so that you dodge them. But, of course, the best way to survive a volcanic eruption is to not be near the volcanoes. But, even if you're really far away from the volcano, you could still be affected. So, for example, the eruption of Becky in Iceland 1983 to 87 affected the entire northwest Europe. And that's because all the gases that from this eruption were brought across Europe. So there was sulfur in there, and that accumulated in the plants, which accumulated in the animals, which accumulated in the humans, and there were a lot of deaths because of that, and of course famine as well. There was also, 200 years ago, an eruption of Tambora in Indonesia. Now this was a huge eruption on a massive scale, and this caused global temperatures to drop across the whole entire northern hemisphere, which caused a year without summer, and actually caused cooling of the global temperature for 3 years. So this caused major famine across the northern hemisphere. So we can't obviously forget this wonderful volcano, the unnamable Icelandic volcano, 5 years ago, which swept ash across the UK and closed UK airspace for 3 days. So this volcano, the ash from it was able to affect us here in the UK because it was incredibly fine. And that's more because it involved an eruption that involved magma and water interacting together. So when water comes into contact with magma in a big way, so like this eruption occurred beneath the glacier, you will get the water will flash to steam, and so if our iron brew bottle was normal fragmentation of a magma, you'd get enhanced fragmentation, causing much finer material to be produced by water being added with this as well, or steam. So these are hydrovolcanic eruptions, which used to be called phreatomagmatic eruptions, and these are incredibly explosive. So these are actually responsible for some of the largest eruptions that we know of. So the cataclysmic end of the Krakatoa eruption in 1883 was actually so explosive because it involved seawater coming into contact with magma in a magma chamber. So this created the loudest sound when it created its blast, the loudest sound in recorded history, which was recorded around the entire globe as a sudden decrease in pressure. These hydrovolcanic eruptions also occurred at the end of the Vesuvius AD 79 eruption, which killed the inhabitants of Pompeii. And so I'm actually studying these hydrovolcanic eruptions, but these were eruptions that occurred around 54.5 million years ago, somewhere in the North Atlantic, and we find these ashes all across northwest Europe, and I'm studying them to try and understand these hydrovolcanic processes a bit more, so that we can also find out like how bad things could get from ice, because the eruptions affect us here. But okay, so volcanic eruptions and volcanoes aren't all that bad. We also have very fertile volcanic soils that people across the world exploit, and we get fantastic minerals, so diamonds, that's a volcanic mineral, as well as amethyst and emerald. We can get our geothermal power from volcanoes, it's fantastic. And also, we can build our volcanoes on them. Our volcanoes. So, yeah. So here we have Edinburgh Castle, and then we have Stirling Castle and Dumbarton Castle, and actually all of these are built on the inner workings of really ancient volcanoes that used to plague Scotland. So that's pretty cool. So I'm just going to wrap up by saying a couple of things. So volcanoes. Well, I've forgotten what I was going to say. Right, so volcanic eruptions occur because of sticky magma that doesn't release the gases and the pressure within it. Or we can have the interaction of magma and water, which create huge explosions. And the best way to survive a volcanic eruption is to find a thick walled, sturdy building, preferably a prison cell. And volcanoes aren't all that bad. We can have volcanic soils, which are really fertile, volcanic minerals, and they're a fantastic place to build your castle. So thank you for listening.
Thanks, Sapphire. That was really good. I know a lot more about volcanoes. Does anyone have any questions for Sapphire? Just I'll take this one.
What happened to that old man? Did he die?
Yeah, he did.
Wow. The cats.
Yeah, I think they probably died as well. Yeah, there were 57 people died in that eruption, which actually isn't too bad for the volcano where it was, but yeah, unfortunately.
So Jenny mentioned that you climbed the tallest volcano in Indonesia. How was that?
So it wasn't the tallest, it was the most dangerous. So it wasn't erupting at the time, otherwise I wouldn't have climbed it.
Right.
But yeah, that was incredibly difficult actually.
Was it cold at the top?
It was, well, it's cold, yeah.
Was that awesome?
Yeah, it was really awesome. Yeah, because we started our climb at 1 AM in the morning, so it was pitch black, and then we got up to the summit for sunrise. So yeah, it was really good. But I'm not doing it again.
Any other questions?
Can you say the name of that volcano?
I used a YouTube video to try and learn it. It's like Eyjafjallajökull, but I'm about to go to Iceland next week, so someone will tell me that's totally wrong.
I think we might just thank Sapphire again, but please feel free to ask your questions at the break, if that's okay with her. Okay.
Okay, so just before the break, we have another Bright Club speaker, Colin MacLeod, who is a research fellow in zoology at Glasgow and Aberdeen, and he will be talking mollusks.
Literally.
Don't punch yourself for a moment. Hi. When I tell people what I do for a living, I always get the same reaction. Usually I've just met them and they shake my hand and they say, "What do you do?" And I say, "I'm a scientist." And they go, "Oh, that's interesting. What do you study?" And I say, "Testicles." For a moment the silences, I try to work out whether they misheard me or not. And then it sinks in, I really did just say testicles. That's when they realise they're still shaking my hand. And they go, "Ah!" It's almost like they think I haven't washed my hands since I last did whatever it is I do with testicles. Which, to be honest, I probably haven't, but that's beside the point. Now, before any of you start getting any strange ideas about me, this isn't a career I necessarily chose to go into. It's something that just one day fell into my lap. It all started when a colleague wandered into my office and asked me if I'd help him weigh his testicles. And I thought I could handle that. Now, when you work at university, this sort of request isn't as unusual as you might think. And I've been asked to do stranger things. Not much, admittedly, but still. I should make it clear, though, when I said he needed help weighing his testicles, they weren't his testicles. It's just he had a pair of testicles he needed help weighing. They were actually porpoise testicles. And if you know anything about porpoise testicles, you know why I needed the help. If you don't know anything about porpoise testicles, don't worry, you'll find out later. Now, that was the experience that got me hooked. Although hooked probably isn't a good word you should use when you're talking about testicles, is it, guys? That was the experience that got me started. And I now stand before you, one of the world's foremost experts in the study of animal testicles. As you can imagine, my parents are very proud of what I've done with my life. You should see my mum when somebody asks her what I do for a living. I think she'd prefer if I did something she'd more happy telling people about, like being a drug dealer, or a serial killer, or a Tory. Okay, I went too far there at the time. Anyway, unlike my mum, I'm proud to be able to say my research is quite literally bollocks. Some days it's dog's bollocks, but I study other species as well. And what I look at is why different types of animals have testicles of different sizes relative to the size of the rest of their bodies. At this point, you're probably thinking, that different animals really differ that much in the size of their balls. After all, surely a bollock is a bollock regardless of the species. Well, I've looked at a lot of testicles in my life. I bet that's something you weren't expecting to hear tonight at a science event. Anyway, I've looked at a lot of testicles in my life, and I can tell you there's a lot more variation out there than you might think. And this is really what I want to share with you tonight. But before we can do that, as good scientists, we need a baseline to compare the different species to. I'm going to start off with the species whose testicles you're most familiar with. Or at least I hope it's the species whose testicles you're most familiar with. Humans. If you're more familiar with the testicles of a different species, I don't need to know about it, okay? So, humans. Let me just get my plums out so you can see how big they are. Don't worry, I don't mean my plums. There's one thing I've learned in all my years of being a scientist, is that a surprisingly large number of people really don't appreciate it when you get your testicles out in front of them. Even if it is in the name of science. So, I brought something along that will give you an idea of their size. So there we go. Testicles of the average adult human male really are about the size of a pair of plums. Gentlemen, if you want to verify this, feel free. Obviously not with mine, but with your own.
Right.
Ladies, if there's a man sitting next, just reach across and obviously don't do this if you don't know the man. Be polite and introduce yourself first.
Yeah.
So, that's the human baseline. I'll just put my thumbs down on the table over here for future reference. So how do we compare to other species? Well, if I was a male gorilla, my testicles would be this size. You might not know to look at them, but male gorillas have got really small balls. And while we're on the subject of gorilla genitalia, and there's another phrase I bet you never thought you'd hear tonight, while we're on the subject of gorilla genitalia, they've got really small penises too. Only about a quarter of an inch long when fully erect. So now you know why female gorillas always look so pissed off when you see them in nature documentaries. There's also a good chance you'll never be able to look at a cherry tomato again without thinking about gorilla testicles. I can only apologise for that. But, armed with this knowledge, you now know if you want to insult a man and get away with it, simply tell him you think he must be hung like a gorilla. 9 times out of 10 he'll look really pleased with himself and agree with you, because he won't realise you just inferred he's got a tiny little penis. Now, before the men in the audience start getting too cocky, and you pardon the pun, humans don't have the biggest testicles relative to the body size, not by a long way. If I was a male chimpanzee, our closest living relative, my testicles would be this size. Here the women in the audience go, ooh. Here the men doing it too. Now, In case you're wondering why, this is because female chimpanzees are, and I mean this in the nicest possible sense of the word, sluts. There's really no other way to say it. They'll trade sex for food, for protection, because they're bored. They'll have sex with pretty much any male that asks. Now, like all men, male chimpanzees want to ensure that the father of any offspring they're raising. And that means they've got to produce an awful lot of sperm to compete with all the other sperm from all the other males that's sloshing around inside any female they mate with. And to be able to do that, they need these really big bollocks. Now, at this point, most of the men in the room are probably feeling quite relieved they're not chimpanzees. And not just the whole girlfriend trading sex for food thing. Although if that's what floats your boat, who am I to tell you that you're wrong? You are, who am I to tell you? No, most men are glad they're not hung like chimpanzees, because carrying a pair of this size around with you everywhere you went would be a right pain in the, well, bollocks. But chimpanzees are nothing. Take, for instance, I always wince when they drop in there. Take, for instance, the humble and otherwise rather unremarkable harbour porpoise. The species that got me into studying testicles in the first place. Now, for those of you who don't know, a porpoise is kind of like a small, boring dolphin that doesn't do any of that leaping around, or tricks, or any of that flashy show-off stuff we usually associate with dolphins. If I was a male, the male harbour porpoise has testicles that are 4% of its total body mass. Now, that won't mean that much to you until I put it in some sort of perspective. I weigh about 13 stone. If my testicles were 4% of my body mass, they wouldn't be the size of plums or of oranges. They would be the size, like a mono microphone stand.
Good.
And I'll just hold them up for the people at the back. They'd be the size of watermelons. And now you can see why my colleague needed help weighing the pair he had. And maybe this explains why they're quite so boring. After all, guys, would you be able to do much leaping around with testicles like this? In fact, my guess is not able to do much of anything. Could you imagine how difficult it would be driving a car with testicles like this? The damn things would be jammed in the steering wheel whenever you try to turn a corner. I can see a few of the men in the audience wincing at the very thought. And spores would probably be out of the question. After all, people would keep getting confused as to which one was a real ball. Could you imagine how painful it would be getting kicked in the goalies if they were this big? Gets worse. And sex would probably be pretty difficult too. I mean, think about the simple, tender, loving act that is the blowjob. Which, some man with a microphone stands laughing at it. For testicles this size, one wrong move you'd end up getting your 2 black eyes. And probably a fractured skull to go with it. And that would take an awful lot of explaining when the ambulance arrived to carry them off to hospital. Really, with testicles this big, I'm going to have to put these down before I drop them. I really don't know how the porpoises do it. Hats off to them. Really, with testicles that size, pretty much all you'd be able to do is lounge around on the sofa all day, playing computer games and watching football, and occasionally summoning up the energy to drag your testicles through to the fridge to get another beer. Of course, for some men, that's not that much different from what they do most of the time anyway. And this is the most important thing I learned all my years studying the testicles of hundreds and hundreds of different species. That's not because such men are secretly hung like porpoises, or chimpanzees, or for that matter, gorillas with their tiny little penises. It's because, and this one little bit of information will completely change the way you view such men forever. It's because they're lazy bastards. Thank you very much.
Thank you very much. Does anyone have any questions?
Okay.
Porpoise ball point.
That is a very good question. Next time James is in the bath trying to do his chemistry, I'll give him a pair to take in there. He can tell me whether they do. That is a really good question.
Don't know.
I think I now have my next research paper. Thank you very much. Just give me your name and the violation. I can add you as a footnote.
Not even a quarter.
Why do some voices have such big holes?
Now, somebody always asks that question, and we don't know. They are so much bigger than anything else in almost any other mammals of a similar size that it's just beyond everything. And we really just don't know why this is. There's been a few theories over the years, one of which is that because they're buoyant in the water, they can get away with carrying these really big testicles around. But that doesn't really hold true because other things that live in the water don't necessarily have big bollocks as well. But again, that will be another paper of mine at some point in the future, and may yet win me an Ig Nobel Prize if any of you know what Ig Nobel Prizes are. I can't see it not if you're doing something testicles the size of watermelons. Do we have time for one last question?
What's your favourite pair of bandals?
My own. I was going to say, if you want to verify this, you can meet me in the bar afterwards, but I'm not going there. Sorry, that's.
Okay, we're going to take a 15-minute break.
Yep.
So you can all get more drinks or food or whatever you like, but come back in 15 minutes because we get to hear about impact craters and chilies.
So I know where the ladies is. Where's the gents?
Actually, I like standards. It works really well.
So some prizes, prizes for you.
Oh wow.
It's not, don't hold it around.
Thank you.
Yes. Okay, on the Ig Nobel. Ig Nobel.
Yes. We have actually a really good working theory, but there's so many of them supporting it. But there's always the best moment for any theory.
I'm a sort of a citizen scientist. My last paper gets published in Humble Research.
Oh, Pianos and Probable Research. Yeah. What was that one?
One of my interests is a snake. So back in November, myself and my co-guys in France found it's one of the evil publishers that also were selling languages. So we did a full system of pages.
Interesting idea.
7,000 views. It's been a week.
Now, are you sure that this isn't copyright material from John Cage that they just published? John Cage. He did 433, which is just silence. Yeah.
Anyway, but a very silly stuff. So we submitted it to the Journal of the Universal Rejection. We rejected it. So we actually accepted for public use.
It's always one of my more favourite journals in global research. The Journal of Irreproducible results.
Yes. Hey, we've got one of the last big tweets. We're talking complete bollocks.
We have this beautiful Pint for you.
Thank you very much.
It's also this wonderful Monday that's full of things.
Thank you.
Many of which are also related to my friends.
Really? Thank you very much.
Thank you. That was.
Yep.
Thank you. Thanks.
Sorry, beloved, lovely.
No, so Sarah is on before you for 20 minutes.
Oh, right, okay.
Yeah, it's a wrong mark.
Yes.
She would.
You know if you want one or not. Hello. Oh, hello. You're right. I was wondering if you'd be here or not. I don't know. Aaron was like, well, I know, well, when I said subjects, actually, and I was like, I've done it, but on the other hand, it's just that time. Well, I did it last year, didn't I? So I did it last year, yes, it's my fault that you kept getting all the posts. And my fault you kept getting the posts. I was like, yeah, it wasn't bad. They definitely missed a trick. It's a renewable conference. And apart from my little contribution to the uni and staff, I'm not going to do that, which is really new, but we're part of the geothermal research team, so I thought we could start out and say, right, okay, next year, so it's him. Oh, yeah, well, he's part of geothermal as well, so yeah. Taking on way too much. Oh, yeah, but I see my field work next year. Yeah, in I've been slowly getting lots of grants in
Yeah, you have to. So, and then if you get it as an exploration, I'll take 7 yeah, with the, you know, the expeditions, you know, the translation privilege here for it's the same sort of, yeah. I know, they're teaching me that.
First time that I've been in here, I got lost right away.
Hang on. If not, for no reason. I know she's
Well, okay, that's kind of ready. Hang on a minute. How do I switch my computer to?
Are you manning a ticket stand?
How do I switch my computer to not? Mirror displays. That's it. Yeah.
Just these to is it? We got a bright compass.
It's there, and then the right covers it.
Okay, cool.
You stand up like
Snappy's experience, not just like told secondhand.
We'll be starting in about a minute, so if you're waiting at the bar, hurry up and get your drink.
It's alright,
I'm sorry, I can't hear people who hug my flatmate and not me.
I gave you a hug yesterday.
He patted my... He went like this. And I go,
She gets the same treatment.
I gave him a hug. He went, and when he got worried, he was like, "Hooray! Oh no, it's too late.
No.
It's too late."
You're gonna get this hug when you're like. See, now you don't want it. Now you know.
That's because I said no this time. Just because I wanted a hug yesterday doesn't mean I want a hug today.
Why can't you learn from her? No hugs.
Yeah.
The rule Rory is hugs when I want
Okay, we're ready to start our next talk. So our next speaker is Sarah Simpson. She's a master's student at Glasgow University studying impact hydrothermal systems. She is fascinated by impact craters and their potential for creating habitable environments for life, both on early Earth and on other more hostile planets. She uses stable isotopes to reconstruct ancient environments and conditions in impact structures. So
without further ado, this is Sarah talking about meteorite impact from ashes to microbes.
There we go. Good evening. Thanks for sticking around. So yeah, like Andrew said, I'm a master's student finishing up at Glasgow Uni. I'm actually a geologist, and right now I'm studying earth science. Kind of a crossover between chemistry, biology, geology, kind of mixture. So I'm going to tell you guys about impacts and what they can do for you, or maybe what they have done in the past. I don't know. So for the uninitiated, meteorites basically are fragments of rock, ice, metal, a mixture of all three maybe, which actually they survive passage through the Earth's atmosphere and hit the surface. And before it hits the Earth's surface, it's actually called a meteor if it enters the Earth's atmosphere. Before that, if it's just orbiting around, it's called a meteoroid. And this happens quite a bit. There's a lot of stuff floating around out there. About 90,000 kilograms of material enters the Earth's atmosphere every single day. Only less than 1% of it actually survives. And most of this material isn't recovered. So, I mean, the Earth is mostly water to begin with, so most of the stuff falls into the oceans, lakes, whatever. A lot of it falls on land, and Earth is has an active environment. We have an active atmosphere, we have weather, and a lot of this material isn't stable on the Earth's surface, so it just erodes. Every once in a while, though, the larger, faster-moving asteroids, comets, what have you, actually do make it through the Earth's atmosphere, and they hit the Earth's surface and they create impact craters. Right now, as of yesterday, there are 188 impact structures on Earth. This number changes quite a bit. We're discovering new impact craters every day. It's a fairly young science. Only within the last maybe like 40, 50 years or so we've been studying impacts. And we categorize them based on the size, which are called simple craters, the smallest ones, up to what are called multi-ring basins. We don't get these very often on Earth. If you want to see a multi-ring basin, you can look at the Moon. And a lot of that's just due to the fact that Earth doesn't preserve impact craters very well. We have a very active environment. We have plate tectonics, and our crust is constantly being recycled, so we don't see them very often. And impacts are one of the most ubiquitous processes in our solar system. Anything with a solid surface things are going to hit each other. There's loads of crap floating around out there. Impacts happen to everything with a solid surface. And we spend millions of dollars, pounds, euros, what have you, exploring impact craters on Earth and on other planets. And apart from damage control, wanting to know if we're all going to die, tomorrow from an asteroid impact, impacts also produce valuable resources. So almost 40% of the world's gold comes from an impact crater in South Africa. And this is in the entire history of extracting gold. A lot of it comes from an impact structure. Oil as well, a lot of precious gems. Impacts do a lot of weird stuff to the Earth's surface. And I'm going to talk to you guys about that today. And apart from that, impacts tell us a lot about the history of our solar system. I mean, impacts they're responsible for the creation of our moon. And they help shape the Earth as well. So we want to know where we came from. We want to know the history of our planets. And they're not frequent anymore. About 4 billion years ago, impacts were a really common thing when the solar system was still accreting, but we don't see them too often anymore. So just to give you guys an idea of the sizes, the energy, and the frequencies of impacts, a meteorite the size of about 20 to 25 meters in diameter will create an impact of basically nothing. Most of this stuff just gets evaporated into the atmosphere, it just disintegrates on entry, up to about 450 meters. These are just relative sizes. So this changes drastically depending on the composition of the impactor. And that small of a meteorite will cause that releases enough energy, or the same amount of energy between 20 and 30 Hiroshima bombs. It's a huge amount of energy, and that's for really small size as well. And this only happens about 300 to 400 years. You guys might remember, but a couple years ago, the Chelyabinsk meteor in Russia. This was basically an airfall. A meteorite entered Earth's atmosphere and exploded. It was about 18 miles above the surface of the Earth. About 1,400 people were injured, windows were blasted. A lot of people thought it was a missile, but it was a meteorite. And a little bit of this actually fell to the Earth. We recovered quite a bit of it, but it didn't actually create a crater that we're aware of. If you step it up a little bit, between 50 and 90 meters, a meteorite would create about a 1 to 2 kilometer impact crater. And this is equivalent to, similar to what Sapphire was talking about, Mount St. Helens blast. And this happens about every 2,000 years. So this has happened a couple times in its history, but not recently. Even more, 1 to 2 kilometer meteorite. It's going to release more energy than the total annual energy budget released from Earth. Volcanoes, plate tectonics, huge amount of energy. This happens every 350,000 years. You go even further, you're going to basically have mass extinctions, wipeouts. And this only happens about 150 million years. So we haven't seen many of these. There aren't many that exist today, and many impact craters. So just on Earth, another air blast event was the Tunguska event in Siberia. This was about 100 years ago. Similar to what happened in Russia a couple years ago. We have the Barringer crater in the States, which is about 1 kilometer. That crater is about 50,000 years old. That's fairly small, but it's really well preserved, so a lot of people know what it is. They've seen it before. And then you have the largest on Earth, the Bredefort South Africa structure. This is where a lot of our gold comes from, and this is probably the biggest impact crater on Earth. Scientists go back and forth a lot about the size of it. They're a bit ambiguous sometimes, some really old ones that aren't very well preserved. So, are meteorites destructive? Yes, they're very destructive. It's responsible for the extinction of one of the biggest extinctions in the history of our planet, and that was the Chicxulub, depending on who you ask. Everybody says it differently. Maybe it's because I'm American, I don't know. This was about 65 million years ago, so yes, obviously impacts. If something like this happened again today, you would die. And also, a funny thing that geologists like to do, we like to, strange behavior we have, we like to get together and make fun of bad geology movies. Sapphire touched on this as well. So, by the way, if you ever watch these, they're so dumb. Like, they're not realistic at all, but we do enjoy watching them and making fun of them and making ourselves feel better about what we're studying. So yes, they are destructive. But impacts can also be beneficial to the environment. They do a lot of really weird things to the surfaces that they collide with that I'm going to tell you guys about. So, to understand that, we'll first look at how impacts interact with terrestrial surfaces. When I say terrestrial, I mean Earth-like surfaces, not necessarily Earth, but things like Mars, the Moon, solid surfaces, rocky surfaces. So, one, they affect the geology. It's a huge amount of energy is transferred to the surface as heat. You have 3 main stages of impact crater. You have the first, which is contact and compression stage, and this lasts like less than a second. This is when the actual meteorite touches the surface, and you have 2 waves produced as a result of that. You have the initial shock wave, which if you look at movies that have meteorite impacts, you'll see like a first wave come out. People are like, oh god, something's about to happen. And then the second wave comes, and that's called the complementary wave or the release wave, and that's actually produced as a result of a reflection of the first wave, hits the back of the projectile before it vaporizes, and then goes back through the surface, and that kind of unloads all the pressure from the first wave. And pressures can reach as high as 100 gigapascals, which is a huge amount of pressure. And that leads to the second stage, crater formation, which is called the excavation stage, and this is where everybody runs away. So this is when the energy is transferred as heat, and everything basically, all hell breaks loose, everything flies into the atmosphere, vaporizes, whatever. And then you have the modification stage, which is what geologists or planetary scientists are interested in, because this kind of continues until today. Expansion of the crater ceases, erosion and everything, other processes take over, and this is what, in simplest terms, when things stop falling. And the whole process for the biggest impact craters on Earth, 200 plus kilometer diameter, it can take from a couple seconds to 10 minutes for the whole thing to be over with. So it's huge amount of energy, huge amount of heat, and it does some really weird things to the rocks. And as geologists, we've actually have kind of a cult following of impact nerds, where there's a whole area of geology devoted to shock metamorphism, is what we call it, because it's not like anything else that you find on Earth. No endogenic processes, what we call normal volcanism, earthquakes, whatever. Shock metamorphism is in a whole league of its own. And the rocks are called impactites. And they create some really unique effects. The pressures and heat manifests itself in some really interesting ways. So these from slight alterations to the nature of the rock. So you might just be talking about fracturing the rock if you were to throw it off a cliff or something. Similar fractures. To the complete destruction, melting, distortion of actual mineral crystal lattices, vaporization of rocks, melting. You wouldn't recognize the rock if you held it next to an impact eye, what it was before. And what's really important to us is highly shocked rocks and minerals break down really easily. So they don't sit on the surface for very long. They're not stable, so if you were to subject them to normal earth processes, they would weather really easily and break down. Secondly, impacts produce a huge amount of heat. Melted rocks are hot. Don't touch them. That's pretty obvious. You don't want to touch hot rocks. So impacts bring a huge amount of heat to the surface. But they also temporarily distort the natural heat flow on Earth, but look directly beneath the crater. So this is what we call the geothermal gradient. So impacts for a short period, when I say short, it's going to be up to a couple million years, they will distort. So if you were to just go down into the Earth, if you've ever seen the movie Core, it gets hotter as you go down. Not much. But over most of Earth, this is a fairly constant increase in temperature for depth. But impacts can actually make it hotter closer to the surface than what it normally is. And this is great because on tectonically dead planets and moons, impacts can provide a huge amount of heat. This residual heat can last millions of years, essentially. So you've got dead environments, moons that aren't active anymore, planets. Impacts are an external source of energy for these. And more importantly, volatiles. Scientists go crazy over volatiles. Water, volcanic gases, CO2, SO2, hydrogen sulfide. Impacts can evaporate, melt, and release liquids and gases from either crystalline structures, material just sitting in the surface on Mars, for example. Mars has got loads of volcanic gases frozen, water frozen in the surface. And planetary scientists love water because the history of an environment is basically it's recorded in what sort of volatile elements and how much of these elements we can find. And volatile elements provide solvents, chemical reactions. If we find water, you can get all kinds of crazy chemistry going on. If there was a history of it, at least. And also, for future, planetary exploration, we're looking for water because eventually, I don't think the human race, as mentioned earlier, is going to last for much longer. So eventually, we're going to have to move to another planet. So we're always looking for water. And Earth isn't the only planet that has it. Lots of planets and moons have volatile compounds. It's not just Earth. So this is something that, for example, Mars has loads of ice, sulfate mineral or sulfates. We found, this is what Curiosity is doing around poking around on Mars right now looking for. So what we end up with is we get complex chemistry from the breakdown of the impact rocks that are unstable. We get heat and we get circulation of fluid. And we can actually get hydrothermal environments, or a hydrothermal environment. And this is very similar to what we find on Earth. So the Grand Prismatic Springs, you guys might have seen this picture. Those colors that are produced in that spring they're from bacterial mats, what are called cyanobacteria. They're heat-loving, what we call extremophiles. Hydrothermal systems on Earth host a lot of these organisms. You can find them in the deep ocean, you can find them in volcanoes, areas of geothermal activity. And bacteria is not picky. I mean, bacteria is going to live wherever it wants, but if you introduce something like this to a planet, if there's anything living there, if anything was living there, you're probably going to find it anywhere that you have heat and water circulating. So these conditions, obviously, they're conducive to the development of extremophile communities. And impacts actually will temporarily produce these sorts of environments. And they're called impact-generated hydrothermal environments. And they are, in the grand sense, they are temporary. They can, like I said, they're going to last as long as the heat is there. So you're only looking at maybe 1 to 2 million years for really large impacts. And we found evidence for this in impact structures on Earth, and this is only within the last maybe 20, 30 years. So, for example, with my work, I've been working on an impact structure in France. That's what this rock is down here. So we have what are called carbonate minerals and sulfide minerals as well. So I do stable isotope work on these and try to reconstruct environments based off of the temperatures that I'm getting from some of the elements in these. We have about a third of impacts on Earth have actually shown evidence for this activity. So we know this happens. We know impacts on Earth, they've provided these sort of micro niches for basically that are ideal environments for organisms to live. And they're short-lived, like I said. As soon as the rocks cool and the heat exhausts, you're really looking at maybe a couple million years for really large impacts. But we have found life in impact craters on Earth. This is very, very recent. This is only in the last couple of years. We've actually found fossils. We found impact glasses that were basically eaten away at by what are called siliceous organisms, so bacteria and smaller organisms that eat away at the silica in the impact glass. This is really neat. I think this was only last year. My work, so we can actually find fossils in these rocks. Minerals that are forming as a result of biological activity. So for those of you who may not be chemists, stable isotopes, very, very simply put, are basically different flavors of elements. And it's a different number of neutrons in the nucleus, and depending on the number of neutrons in the nucleus, an element will behave differently. But the flavor, quote unquote, of the element can tell us where it formed, the element's history, the temperature, the pH that the element came from, basically, or what it's been through. And the minerals that I'm studying in the impact crater that I'm looking at have shown that they've been precipitated as a direct result of biological activity. So bacteria that were in the system help precipitate these minerals. And what you would expect, that there's another suite of minerals that I'm looking at, carbonate minerals, have shown that, similar to stable isotopes, that it is a warm environment. It's favorable. pH and the temperature is what we would be looking at for some of these bacteria to live. So that's what I do. And again, this is only in the last couple of years people have really started looking at this. Anyway, so just to close, solar system exploration. In order to understand what's going on in other worlds, we need to understand what's going on in our own first. If we want to study, when we go study Mars, the Moon, other planets and satellites, for example, if we don't know what happens on our own planet, you can't figure out what's going on elsewhere. And yes, impacts are dangerous, but they also create valuable resources. Like I said, they bring energy and heat to otherwise dead environments. And they have the potential to preserve life on other planets. They certainly preserve life on Earth. So when we're poking around on Mars, the Curiosity rover, for example, is poking around Gale Crater at the moment, and it's looking at very similar stuff to what a lot of us impact nerds are looking at. They're looking at hydrated minerals, minerals that have water in them, trying to figure out the history of the rocks in the impact crater. And it's a hot spot for space exploration. So when we look at other planets and satellites, we want to follow the water, and that's exactly what impacts provide. They provide an environment where you have circulation of water, heat, you have a lot of complex chemistry going on. And but a lot of the moons, Titan and Europa, for example, Titan's one of Saturn's moons, and Europa is one of Jupiter's moons. Europa has a huge layer of ice, thick layer of ice on top of it, and a liquid ocean beneath, and it has these really weird features on it. And this is, actually, I was at a conference earlier this year, and NASA announced that they were going to be funding a mission to Europa, which scientists have been really pushing for the last couple of years. Because we've been on Mars for a while, we know basically what's on Mars, but a lot of the more exotic moons we're looking at, Titan, for example, has hydrocarbons, lakes on it. So there's a lot of really weird stuff going on in our solar system. We're just barely starting to scratch the surface. And also the Rosetta and Philae missions we were there earlier last year, we landed on a comet, which is really cool. We've never done that before. It took years to get there. So anyways, that's all I got for you. I'll answer any questions.
Do you have any questions for Sarah?
is there much of a difference in what science are coming with something that impacts on the community, like a huge extinction event, depending on if it hits like land or ocean?
Either way, if you're looking at an impact, a meteorite that's bigger than 10 kilometers, you don't have a chance anyways. I mean, even if you weren't in the direct line of the impact, the tsunami, it would create, you just wouldn't survive. So, it depends on this is, without getting too complicated, what the meteorite is actually made out of, how big it is, what it hits, it all goes into that. But there's a certain size threshold that if you got above that, you just don't have a chance. Great. Sorry.
Of all the films that you've seen, which one has got the worst trilogy?
Oh my god. That's really tough. I liked Armageddon as a kid, and then when I got to a certain age, I was like, oh, this is bad. But it's between Armageddon and the Core, because it's just ridiculous. So.
Thank you, Sarah. Okay, I'm just going to introduce our next and our final Bright Club and final speaker of the night. So this is Pete Gwynn, everyone. And he's going to talk about the science of chilies. So I'll hand over to Pete.
Go on. I don't have chili sounds. Yes, I'm going to talk about chilies. Yeah, you heard. Not just chilies, obviously, that would be stupid. Chilies, and then pain, and then chilies again. And then an incident that happened once. Chilies again. A dinosaur. Oh, sorry. Chilies one more time, and then I'm going to give you a cocktail recipe, and then we can all leave. So the reason I want to talk about chilies is because scientists have been studying them for a while. Partly because they're sort of interesting chemically, but mostly just because they taste weird, and that's fun. Relatively, if you're a scientist. But they're fun partly because they taste very good, and partly because they've got this this chemical in them, which is it's a painkiller, right? But don't overinterpret that. Definitely for the time being, if you break your leg or something, like the hospital. That's not just a code. Because people have made that mistake before, and I've been blamed, and I don't want that on my hands. So the chemical in question is called capsaicin, and it's the same chemical that causes that kind of burning sensation in your mouth when you eat the chili. Yeah? I know what you're thinking, and it's disgusting. My eyes are up there. No, but you're thinking, how can you take pain away with something that causes pain? And the answer is relatively simple. It's all to do with the administration. Sort of how much of the chemical you deliver, how often, where to. It's all in the delivery. Which is why I started doing stand-up. Because when I say that we've studied these things, I mean we, broadly speaking. I haven't. I'm a very lazy man. So basically, other people have studied them. I studied. Whoa, hello. I mean, right, I've been heckled in the past. But I've never had someone actively try and rip the microphone out of my I don't know how far I can walk. I'm worried about ripping out my own hand. That's it. This is as far as I can go. So I'm sorry, sir. This is as far as I can go. Oh, no, it turns out we can go. Right. The point is, I'm going to do an experiment to sort of demonstrate ways of sort of changing the delivery of this chemical. I'm doing a little experiment with you. Not strictly with you, because I'm not allowed to experiment with people anymore. I'm going to do a sort of an experiment near you. So you don't have to join in. Legally, you do not have to join in, sir. You can if you like, and morally, maybe you should. All I'm saying, all the ingredients are there. Ever since the incident, I've not been allowed to do experiments on people. So, the experiment is relatively simple, and it concerns the chili. Because, like I said, the chemical in the chili that you can use to take away pain is the same one that causes that kind of sensation when you bite into the chili. Not that I'd necessarily recommend that. So when you bite it, it's not really a flavour, is it? It's more. It's more sort of visceral than that. It's more sort of a burning sensation. And so, in this situation, what a lot of people would, maybe not this exact situation, but in a situation something like this, what most people will do is drink water to take away the considerable burn. And what that proves is that most people are idiots. Because water doesn't really help. If anything, it makes things slightly worse. It definitely makes things worse. And it's because of some chemistry. I don't like it any more than you do. But basically, the chemical in the chili that causes the burn is it's like a sort of a ring with a long wiggly tail, and things with long wiggly tails don't dissolve in water. I don't make the rules. But if you imagine like fat and like oil and water don't mix, like they think. Or imagine a dinosaur in the bath. It doesn't dissolve, does it? Kind of sits there. Looking at it. So you have to use something else to dissolve the paint away. So you have to use something with like a lot of fat. Fat dissolves it. I'm using milk. Not really because it's got an associated joke, just because it helps, and there's only so long you can talk for. Milk has a lot of fat in, which does dissolve away the things with the long tails. Imagine, say, a dinosaur fondue. Cheese or chocolate, your choice. Either way, the dinosaur would just dissolve away. Give it a kind of a nutty flavour. Milk, of course, not your only option. My final option is vodka. Vodka, my final option. Both in this experiment and also just sort of generally. So I'm using, if you want to replicate this experiment at home, and why wouldn't you? I'm using Glen's triple distilled Scottish vodka. And as you know, so this works in like two ways. The first is, again, the alcohol dissolves away the chemical, and the second, if you've ever been a student, you'll be familiar with this. if you drink enough of Glenn's triple, if you drink enough of Glenn's triple distilled vodka, you really stop being able to feel like most things. Which is good for this situation, or like exams and stuff. So I said that I'd give you a recipe before I left. So maybe, sir, you could mix it up a little cocktail. It's very easy. Here you go. Here's the ingredients. The ingredients are very simple. If we could start with some vodka, please. It depends what sort of a day you've had. Quite a lot. Thank you, sir. Yeah, right, keep going if you like. The second ingredient, predictably, is some milk, please. Some milk, please. Not the chilies. Yeah, fine. You did fill most of it with vodka. So, thank you very much.
You're fucked.
Here's the offending drink. Of course, the drink is relatively simple. What's very important is the garnish. And if at this point you'd like to just pop me a little chili in there, sir, thank you very much. Here's the finished product. I call it the dinosaur martini. And if anyone's interested, I'll be selling them in the foyer afterwards. So there's a trick, basically. There's a trick to drinking these, and the secret is very much to start with the chili, and then you can use the drink to take away the pain of the chili, and then the chili to take away the pain of the resultant hangover, and then you have more of the chili and more of the drink, and the drink and the chili. And so far, it's been 3.5 years. I can try and answer questions, unless they're about cricket. I've really got no chance. So maybe if you've got any questions, buy a dinosaur martini, and I'll see you up there. Cheers.
Okay, so thank you to our last speaker. He was serious about the questions. So that actually concludes our Pint of Science for this evening. I would love to remind you all to come buy tickets for tomorrow's night here, but we've actually sold out, so if you don't already have tickets, you're out of luck. There are other Pint of Science events, so you could go learn about biology or something. Psychology, technology at different pubs, which I haven't memorized, but we have Googled. One of them's at the Dram. If you turn up at the Dram tomorrow, something sciencey will be happening. Also, if you turn up here and have a ticket, sciencey things will be happening. And if you turn up here and don't have a ticket, we'll tell you to go to the Dram. So thank you all again for coming. Please feel free to stick around and question our speakers. He is still there. He's just hiding. And yeah, have a lovely evening. Woo!